Everyone is wrong about Mars. The red planet captures our imagination with its rusty landscapes and ancient riverbeds. Meanwhile, the real prize orbits Jupiter in silence, Europa. No human has seriously proposed going there. That might be our greatest mistake. And here is a question. If aliens are watching us right now, what do you think they're thinking about humanity? Let me know in the comments. I will pin the most creative answer. Now let's begin. The debate between Mars and Europa isn't just about picking a destination. It's about understanding what we're actually searching for out there in the cosmic ocean. Are we looking for fossil evidence of ancient life? Or are we hunting for something alive right now, thriving in conditions we can barely imagine? Mars has been humanity's sweetheart since the 1800s, when astronomers thought they saw canals etched across its surface. Even though those canals turned out to be optical illusions, the dream never died. We've walked on its surface through our robotic ambassadors. We know its chemistry, its geology, its dusty pink skies. Mars feels familiar, almost comfortable in its alienness. But Europa is wild, it's dangerous. It orbits Jupiter, the solar system's monster planet, through radiation fields intense enough to fry any spacecraft that lingers too long. Its surface temperature hovers around -160 degrees Celsius. And yet beneath all that ice, something extraordinary might be happening. Let me share what we've learned just in the past 2 years, because the story has changed dramatically. NASA's Juno spacecraft, which has been studying Jupiter's system since 2016, made a close approach to Europa in September of 2022. The data from that flyby took months to analyze, and when the results came out in late 2025, they rewrote our understanding of this moon. Using Juno's microwave radiometer, scientists measured something we've been debating for decades. How thick is Europa's ice shell? Previous estimates ranged wildly from less than 1 kilometer to over 50 kilometers. That's not a margin of error, that's scientific chaos. But Juno's instruments finally gave us real numbers. The ice shell averages about 29 kilometers thick, give or take 10 kilometers of uncertainty. 29 kilometers, that's 18 miles of solid ice between the surface and the ocean below. To put that in perspective, if you drilled straight down through Europa's ice, you'd have to go deeper than the altitude commercial jets fly on Earth before reaching water. That's not a thin, frozen pond. That's a world-spanning glacier hiding an entire ocean ecosystem. But here's where it gets fascinating. The same instruments detected something else. Scattered throughout that ice, extending hundreds of meters below the surface, are cracks, pores, and irregularities. Think of them like fractures in ancient glacial ice. Except these aren't ancient, they're active. Europa's surface is constantly being tortured by Jupiter's immense gravitational pull, flexing and cracking like a stress ball squeezed in a giant's fist. Those cracks matter enormously. They might be pathways, not pathways for us, but pathways for chemistry, for nutrients, for oxygen generated at the surface by radiation to somehow, maybe, possibly, reach the ocean below. Every planetary scientist studying Europa wants to know, do those surface cracks connect all the way down? Are they transport highways between two worlds, the frozen exterior and the liquid interior? And speaking of what's on that surface, here's something that would have sounded like science fiction just months ago. In January of 2026, researchers analyzing old data from NASA's Galileo spacecraft, which orbited Jupiter from 1995 to 2003, found something they'd missed for over 2 decades. Hidden in the spectroscopy data were faint signals of ammonia-bearing compounds near fractures on Europa's frozen surface. Why does ammonia matter? Because ammonia is a nitrogen-bearing molecule, and nitrogen is one of the essential elements for life as we understand it. You need carbon, hydrogen, oxygen, and nitrogen to build the complex organic molecules that make biology possible. Finding ammonia on Europa's surface suggests it's being delivered from below, either from the subsurface ocean itself or from shallow reservoirs within the ice. But there's another reason ammonia is exciting. It acts like antifreeze. It dramatically lowers the freezing point of water. If Europa's ocean contains dissolved ammonia, it could remain liquid even in conditions that would normally freeze solid. And ammonia doesn't last long in the space environment. It breaks down under radiation. So detecting it at the surface means it was placed there recently, geologically recently, which could mean within the last few thousand years or even more recent. Now, if you're thinking this all sounds incredible but also incredibly difficult to confirm, you're absolutely right. That's why NASA launched the Europa Clipper mission in October of 2024. This spacecraft isn't messing around. It's the largest interplanetary probe NASA has ever built for a planetary moon mission, and it's currently speeding through space on a journey that will take nearly 6 years. Europa Clipper won't arrive at Jupiter until around 2030, but when it does, it's going to change everything. The mission plan calls for approximately 50 close flybys of Europa, each one diving through the moon's tenuous atmosphere and intense radiation environment to gather data that's impossible to collect from a distance. The spacecraft completed its first close approach in December of 2024, passing within just 25 kilometers of the surface. That's closer than many satellites orbit Earth. And the preliminary data has already started challenging our models. The magnetometer detected localized magnetic disturbances near Europa's south polar region, patterns consistent with active plume activity. Not steady, uniform geological processes spread across the moon, but focused, dynamic hotspots where something is actively happening right now. Think about what these plumes mean. If Europa is actively venting material from its subsurface ocean into space, we don't necessarily need to drill through 18 miles of ice to sample that ocean. We could fly through the plume. We could collect particles that were literally inside Europa's ocean moments before. It's like the moon is offering us free samples. The Europa Clipper carries 9 scientific instruments designed to analyze everything from ice composition to magnetic fields to surface geology. One of the most powerful is a mass spectrometer that can identify the chemical fingerprints of organic molecules. During that December 2024 flyby, it detected organic compound signatures with a clarity that earlier observations from telescopes couldn't achieve. We're not talking about life. We're talking about the building blocks that might create conditions where life could exist. Let's zoom out for a moment and look at the bigger picture, because understanding Europa requires understanding its cosmic neighborhood. Jupiter isn't just a planet. It's a miniature solar system unto itself, with 79 known moons orbiting in a complex gravitational dance. 4 of those moons, the Galilean satellites discovered by Galileo Galilei in 1610, are worlds in their own right: Io, Europa, Ganymede, and Callisto. Europa sits in the second orbital position, caught between Io's volcanic fury on the inside and Ganymede's massive gravitational presence on the outside. This position is crucial because it subjects Europa to something called tidal heating. Jupiter's gravity pulls on Europa as it orbits, but so do the neighboring moons. Europa's orbit isn't perfectly circular. It's slightly elliptical, which means the moon gets stretched and squeezed rhythmically as it travels around Jupiter. Imagine taking a rubber ball and repeatedly squeezing it in your hand. Feel how it warms up? That's friction converting mechanical energy into heat. The same process happens to Europa, except the forces involved are planetary in scale. That tidal flexing generates enough heat to keep a global ocean liquid despite being 5 times farther from the Sun than Earth is. We're not talking about a little warmth. We're talking about enough energy to potentially drive hydrothermal vents on Europa's ocean floor, similar to the black smokers we find in Earth's deepest seas. And those hydrothermal vents on Earth, they're teeming with life. Not life that depends on sunlight and photosynthesis, but life powered by chemical energy, by chemosynthesis. Microbes cluster around these vents, feeding on hydrogen sulfide and other chemicals belching from the seafloor. Larger organisms feed on the microbes. Entire ecosystems exist in perpetual darkness, completely independent of the sun. If Europa has similar vents, and the physics suggests it should, then it could host similar ecosystems. We're not talking about fish or whales or anything complex. We're talking about microbes, possibly archaea or bacteria-like organisms that could survive in extreme conditions. But even simple microbial life discovered on Europa would be the most profound scientific finding in human history. It would mean life isn't unique to Earth. It would mean the universe might be far more alive than we ever imagined. Now, before we get too carried away with Europa excitement, we need to talk about Mars, because Mars has some serious advantages that we can't ignore, and honestly, the comparison isn't entirely fair. Mars and Europa are solving different problems. Mars is accessible. It's relatively close to Earth, with launch windows opening every 26 months when our planets align favorably. The journey takes about 7 months with current technology. We've been landing things on Mars since 1976, when Viking 1 touched down. We know how to get there. We know how to survive there, at least robotically. Europa? Europa is incredibly far away, orbiting Jupiter at a distance of about 628 million kilometers from the Sun at its closest approach. The journey takes years, not months. And once you get there, you're operating in one of the most hostile radiation environments in the solar system. Jupiter's magnetic field traps charged particles, creating radiation belts that make Earth's Van Allen belts look gentle. Any spacecraft orbiting Europa would be fried in months without serious shielding. That's why Europa Clipper doesn't actually orbit Europa. Instead, it orbits Jupiter and makes repeated flybys of the Moon, diving in quickly to gather data and then retreating to safer distances. It's like studying a bonfire by running past it repeatedly rather than sitting next to it. Efficient? Yes. Easy? Absolutely not. Mars also gives us something Europa can't: surface access. We've driven rovers across Martian plains, drilled into rocks, analyzed soil chemistry, and even flown a helicopter through its thin atmosphere. The Perseverance rover, which landed in Jezero crater in February of 2021, has been collecting carefully selected rock samples in sealed tubes. Those samples are sitting on Mars right now, waiting for a future mission to bring them back to Earth. Actually, we need to talk about that sample return mission because the story took a dramatic turn. NASA's Mars Sample Return Program was supposed to be the flagship mission of the 2020s, a joint effort with the European Space Agency to retrieve Perseverance's samples and bring them home for detailed laboratory analysis. By 2024, though, the projected cost had ballooned to around $11 billion, with return dates potentially slipping into the 2040s. In January of 2026, just a few months ago, a congressional spending bill effectively cancelled the program. The White House had recommended ending Mars sample return in favor of prioritizing human Mars exploration instead. Congress shifted some funding to a new program called Mars Future Missions, meant to preserve critical technology development like advanced entry, descent, and landing systems. But the practical consequence is that Perseverance's carefully collected samples are stranded on Mars indefinitely. That's a blow to Mars science, no question. But it doesn't mean Mars exploration is ending, far from it. Other missions are moving forward, including some fascinating international efforts. Speaking of which, if you're curious about what daily existence on the Red Planet would actually involve, I created a detailed video exploring exactly that. It's called What Would Life on Mars Really Be Like? And it dives into everything from radiation exposure to growing food in Martian soil. The link is in the description. the European Space Agency is pushing ahead with their Rosalind Franklin rover, a mission that's had a complicated history. Originally planned as a joint venture with Russia's space agency Roscosmos, those plans collapsed after 2022 due to geopolitical tensions. NASA stepped in to provide the launch vehicle and other critical hardware. The mission is now scheduled to launch in 2028 on a SpaceX rocket. Rosalind Franklin is designed to do something no Mars rover has done before: drill up to 2 meters below the surface. That depth matters because Mars's surface is bathed in harsh, ultraviolet radiation and oxidizing chemicals that destroy organic molecules. But deeper down, protected from that bombardment, ancient organic compounds might be preserved. If life ever existed on Mars, we're more likely to find evidence of it in the subsurface. China is also advancing rapidly in Mars exploration. They successfully landed the Zhurong rover in 2021, making China only the second nation to operate a rover on Mars. They're planning their own sample return mission, though the timeline remains uncertain. The global race to Mars is very much alive, even if NASA's sample return program hit a roadblock. Meanwhile, there's also the Escapade mission, which arrived at Mars in 2026. It's not a lander or rover. Instead, it's twin spacecraft studying Martian space weather, the interaction between the solar wind and Mars's thin atmosphere. Understanding how Mars loses atmospheric particles to space helps us understand how the planet went from a warmer, wetter world billions of years ago to the cold desert we see today. That transformation is central to understanding Mars's habitability, both past and potential future. Here's the thing about Mars that keeps it in the conversation. We have strong evidence that liquid water once flowed across its surface. Extensively. We see ancient river valleys, dried lake beds, minerals that only form in the presence of water. Jezero crater, where Perseverance is exploring, was once a lake fed by a river delta. That delta deposited sediments over millions of years, and those sediments might contain fossilized microbial mats or other biosignatures from when Mars was habitable. Past habitability versus current habitability. That's really the core difference between Mars and Europa. Mars might tell us about life's history. Europa might tell us about life's present. But there's another angle to consider: usefulness for human exploration. If we're thinking long-term about establishing a permanent human presence beyond Earth, Mars has some clear advantages. It has a day-night cycle almost identical to Earth's, about 24 hours and 40 minutes. That matters for human circadian rhythms, for agriculture, for psychological well-being during long-duration missions. Mars has an atmosphere. Yes, it's thin, less than 1% the density of Earth's, mostly carbon dioxide, but it's there. You can use it for aerodynamic entry and landing. You can potentially extract oxygen from that carbon dioxide through chemical processes. You can grow plants in pressurized greenhouses using Martian soil as a growing medium with some amendments. Europa has none of that. It has essentially no atmosphere, just a tenuous exosphere of oxygen created by radiation breaking apart ice molecules. There's no soil, only ice. The surface temperature would freeze carbon dioxide solid, and that radiation environment makes extended surface operations incredibly challenging for both humans and electronics. So if Mars has all these practical advantages, why are we even talking about Europa? Why are scientists so captivated by this distant, frozen, radiation-blasted moon? The answer comes down to one word: oceans. Water is the universal solvent, the medium where chemistry becomes biology. Every form of life we've ever discovered requires liquid water, not ice, not vapor, but liquid water where molecules can move, interact, and organize into the complex patterns we call life. Mars had liquid water billions of years ago, but today It's mostly frozen in polar ice caps and buried as permafrost. The surface is too cold and the atmospheric pressure too low for liquid water to exist stably. Europa, on the other hand, has an entire ocean right now, not billions of years ago. Today, this moment, and it's not a small ocean. Conservative estimates suggest Europa's ocean contains 2 to 3 times the volume of all Earth's oceans combined. We're talking about an ocean roughly 60 to 150 kilometers deep, encircling the entire moon beneath that ice shell. Think about what that means. Earth's deepest ocean trenches go down about 11 kilometers, and we've barely explored them. Europa's ocean could be 10 times deeper, and it's been sealed away from sunlight for the entire history of the solar system. What could evolve in an environment like that? What adaptations, what bizarre and beautiful forms of life might emerge in perpetual darkness, feeding on chemical energy from the seafloor? The ocean chemistry is another fascinating piece of the puzzle. Data from the Galileo spacecraft and the Hubble Space Telescope indicate that Europa's ocean is salty, dominated by sodium chloride, basically table salt, with traces of magnesium sulfate. This isn't alien chemistry, it's remarkably similar to Earth's seawater. The pH is probably slightly alkaline, and the temperature near the seafloor could reach several degrees above freezing, where hydrothermal vents pump out heated, mineral-rich water. Scientists have done calculations on how much chemical energy Europa's ocean could support. Through a process called serpentinization, water reacts with rocks in Europa's mantle to produce hydrogen gas. Models suggest Europa could generate around 100 billion kilograms of hydrogen annually. That might not sound like much on a planetary scale, but it's enough to potentially support methanogen-like microbes, organisms that consume hydrogen and produce methane as a waste product. On Earth, methanogens are among our planet's oldest life forms, thriving in environments devoid of oxygen. They live in deep-sea vents, in the guts of animals, in waterlogged soils. They're incredibly resilient. If similar organisms exist on Europa, they'd be living in conditions not too different from what Earth's early life experienced billions of years ago. But here's what really gets astrobiologists excited: the potential for surface-ocean exchange. Remember those cracks and fractures we talked about earlier? Some of Europa's surface features suggest that the ice shell isn't just a static barrier. It's dynamic, possibly overturning in some regions, bringing deep ice to the surface and pulling surface material down. There's a phenomenon called chaos terrain on Europa, vast regions where the surface has broken apart and reformed into a jumbled mess. The best explanation we have is that warmer ice or even liquid water from below caused the surface to collapse and refreeze in a new configuration. If that's happening, it means there's active communication between the surface and the ocean, at least in some locations. And then there are the plumes. The Hubble Space Telescope has detected what appear to be water vapor plumes erupting from Europa's surface, similar to but less dramatic than the geysers on Saturn's moon, Enceladus. These observations are tricky because the plumes aren't constant. They seem to be episodic, appearing at certain times and locations, then disappearing. But if they're real, and most scientists think they are, they offer an incredible opportunity. Imagine flying a spacecraft through one of those plumes with instruments capable of analyzing the chemical composition of the water droplets and ice particles. You'd be sampling Europa's ocean without drilling through 18 miles of ice. You'd be collecting material that was literally inside that ocean minutes or hours earlier. It's the easiest hard thing we could possibly do. That's exactly what Europa Clipper is designed to attempt during its 50 flybys. The spacecraft carries instruments sensitive enough to detect and analyze organic molecules, salts, and other compounds in those plumes. If the timing is right, if a plume erupts during one of the flybys, we might get our first direct taste of Europa's ocean chemistry within the next decade. Now let's address the elephant in the room. The radiation. Jupiter's magnetic field is 14 times stronger than Earth's, and it rotates with the planet every 10 hours. This creates a powerful magnetosphere that traps and accelerates charged particles to tremendous energies. Europa orbits right through the densest part of this radiation belt. To put this in perspective, a human standing on Europa's surface would receive a lethal dose of radiation in about a day. Electronic components that would last years in Earth orbit might fail in months at Europa. This isn't a trivial engineering challenge, it's a fundamental barrier to exploration. Europa Clipper addresses this with heavy shielding around its most sensitive electronics, a vault of titanium walls protecting the spacecraft's brain from radiation damage. But even with shielding, the mission has a limited lifetime. After approximately 4 years and 50 flybys, the accumulated radiation dose will likely degrade the spacecraft systems beyond functionality. It's built to die doing its job. Any future mission to Europa, especially a lander, would face even harsher challenges. A lander would need to survive on the surface for weeks or months to accomplish meaningful science. It would need shielding, it would need a power source, probably radioisotope thermoelectric generators, since solar panels are inefficient that far from the sun, and it would need to operate autonomously because communication lag time to Earth is over 40 minutes one way. Compare that to Mars, where communication lag is between 4 and 24 minutes depending on orbital positions, and you can start to see why Mars seems more manageable for human missions. You can have something approaching real-time problem-solving on Mars. On Europa, if something goes wrong, the spacecraft is on its own for the better part of an hour before even receiving instructions from Earth. But difficult doesn't mean impossible, and the scientific payoff could be extraordinary. Several concepts for Europa landers are in development. One idea involves a lander that could melt through the ice using a nuclear-powered heating element, descending slowly through the shell while paying out a communications tether. It's called a Cryobot, and it's basically a robotic ice worm. Once the Cryobot reaches the ocean, it could deploy a small autonomous submarine, a Hydrobot, to explore the water beneath the ice. This Hydrobot would be on its own, pre-programmed with decision-making algorithms because controlling it remotely from Earth would be impossible. It would search for plumes of warmer water rising from the seafloor, chemical anomalies, anything that might indicate biological activity. This isn't science fiction. NASA and other space agencies have tested Cryobot prototypes in Earth's glaciers and polar ice. The technology exists. The challenge is making it robust enough, autonomous enough, and reliable enough to work on Europa without human intervention for repairs. The timeline for such a mission is uncertain. Europa Clipper needs to complete its reconnaissance first, mapping the ice shell thickness in detail, identifying the best potential landing sites, measuring plume activity. That data will inform where and how a future lander should be designed. We're probably looking at the late 2030s or 2040s before a Europa lander mission could realistically launch. That seems like a long time, and it is. But consider what we've accomplished in recent decades. In 1995, we didn't know for certain that planets existed around other stars. Today, we've confirmed over 5,000 exoplanets, and we're analyzing their atmospheres for biosignatures. In 2000, we thought Mars was bone dry. Today, we know it has subsurface ice and possibly seasonal briny water flows. The pace of discovery is accelerating. Mars and Europa represent two different philosophical approaches to the search for life. Mars is the detective story, examining cold case evidence from billions of years ago, piecing together what happened when the planet was young and wet and possibly alive. Europa is the live investigation, searching for something that might be happening right now in an environment we've never directly observed. Both are valuable, both are necessary. The question isn't really which one we should choose. The question is how we allocate resources and attention between them in an era of limited budgets and competing priorities. There's something deeply human about the way we approach exploration. We're drawn to the familiar, the tangible, the places we can almost imagine walking ourselves. Mars satisfies that yearning. We can picture standing on its surface, looking at its salmon-colored sky, feeling the fine dust beneath our boots, even through a spacesuit. Europa defies that visualization. It's profoundly alien in ways that make our imaginations stumble. But let's push through that discomfort and really think about what exploring Europa would mean, because the challenges reveal something important about what we're capable of as a technological civilization. Every mission we've sent beyond Earth has expanded our abilities, forced us to solve problems we didn't know existed. Europa would be the ultimate test. Consider the engineering required just to communicate with a spacecraft at Jupiter's distance. At its closest approach, Jupiter is about 628 million kilometers from Earth. At its farthest, it's around 928 million kilometers away. Radio signals travel at the speed of light, which sounds fast until you're dealing with astronomical distances. A message from Europa Clipper takes between 35 and 52 minutes to reach Earth, depending on orbital positions. That communication delay fundamentally changes how we operate spacecraft. Everything must be automated. The spacecraft can't ask permission to adjust its instruments or alter its trajectory during a critical flyby. It has to make those decisions itself using pre-programmed logic and artificial intelligence algorithms that evaluate situations and respond accordingly. Europa Clipper carries sophisticated autonomous navigation systems that allow it to adjust its trajectory in real time during flybys, compensating for gravitational perturbations from Jupiter's moons. It can identify when its instruments are pointed correctly at surface features and trigger observations without human intervention. It's exploring Europa semi-independently, with scientists on Earth more like mission planners than active pilots. This autonomy is essential for any future Europa lander or submarine mission. A Hydrobot exploring Europa's ocean wouldn't have the luxury of waiting 90 minutes for round-trip instructions every time it encountered an interesting feature. It would need to recognize scientifically valuable targets itself, make navigation decisions, manage its power budget, and perhaps most importantly, know when something was going wrong and initiate self-preservation protocols. We're developing these technologies right now, testing them in Earth's oceans and Antarctic ice sheets. Autonomous underwater vehicles can already map seafloor terrain, follow chemical gradients to their sources, and avoid obstacles without human guidance. But Europa presents unique challenges beyond anything we've tested terrestrially. The pressure in Europa's ocean increases with depth, just like on Earth, but because the ocean is potentially much deeper, the pressures at the seafloor could be enormous. At 100 kilometers depth, you're looking at pressures around 140 megapascals, roughly 1,380 times Earth's atmospheric pressure at sea level. That's comparable to the deepest parts of Earth's oceans, but sustained across a much larger volume of water. Any submarine exploring Europa's ocean would need a hull designed to withstand those crushing forces. It would need to be small to save on mass during the long journey from Earth, which means limited space for scientific instruments and an even more limited power supply. Every decision about what to include becomes a painful trade-off between scientific capability and engineering feasibility. Power is actually one of the trickiest constraints. Solar panels are useless beneath kilometers of ice and in an ocean with zero sunlight. Batteries have limited capacity. The most practical option is a radioisotope thermoelectric generator, or RTG, which converts heat from radioactive decay into electricity. RTGs have powered spacecraft for decades, from the Voyager probes to the Curiosity and Perseverance rovers on Mars. They're reliable and long-lasting, but they're also heavy and produce relatively modest amounts of power. A Europa submarine would need to be incredibly energy efficient, using that limited power budget wisely. Propulsion would probably rely on minimal thrust, gliding and drifting with ocean currents when possible. Instruments would power up only when actively taking measurements. Communications with the surface lander, which would relay data back to Earth, would be brief and scheduled. And all of this assumes we can actually get through the ice in the first place, which brings us back to the Cryobot concept. Melting through 20 to 30 kilometers of ice isn't a quick process. Even with a nuclear heat source, you're looking at potentially years to reach the ocean. The Cryobot would need to navigate around obstacles, avoiding regions where the ice composition changes unpredictably. It would need to maintain communication with the surface through that entire descent, probably using a fiber optic cable that spools out behind it. What if the cable breaks? What if the Cryobot gets stuck in a crevasse or encounters a layer of ice too difficult to penetrate? These aren't hypothetical concerns. They're real engineering risks that mission designers lose sleep over. Every single point failure could end the mission. Redundancy helps, but it adds mass, and every kilogram you launch to Europa costs tens of thousands of dollars and requires more fuel. Let's contrast this with Mars again, not to diminish Europa's importance, but to understand why Mars remains attractive despite its potential lack of current life. Landing on Mars is difficult, but it's a solved problem. We've done it successfully 9 times with increasingly sophisticated spacecraft. We understand Martian atmospheric entry. We know how parachutes behave in the thin air. We've tested supersonic retropropulsion, the technique of firing rockets to slow down while still traveling faster than sound. The Perseverance rover landing in 2021 was an engineering masterpiece. The spacecraft entered Mars's atmosphere at about 20,000 kilometers per hour, deployed a massive parachute to slow down, then jettisoned the heat shield and parachute to fire descent engines. At the last moment, it lowered the rover on cables from a sky crane system, gently placing Perseverance on the surface before the crane flew away to crash at a safe distance. The entire sequence, from atmospheric entry to touchdown, took 7 minutes. 7 minutes of automated precision with no room for error. We can do that on Mars because we've built up decades of experience. We've failed, learned, improved, and succeeded. Europa doesn't offer that gradual learning curve. The first mission to land on Europa will be pioneering in the truest sense, venturing into an environment where we have limited ground truth data and no margin for error given the mission cost and transit time. But here's the thing about difficult goals: they inspire us in ways that safe, incremental progress never can. The Apollo program wasn't driven by easy wins. It was motivated by an audacious goal that seemed nearly impossible in 1961 when President Kennedy announced it. Reaching Europa's ocean would be this generation's Apollo moment, an achievement that demonstrates what humanity can accomplish when we commit to a vision larger than ourselves. And the scientific questions we could answer would reshape our understanding of life's place in the universe. Is Earth's biosphere unique, a cosmic fluke that occurred once in billions of years? Or is life common, emerging wherever liquid water and chemical energy coexist for sufficient time? Europa could answer that question definitively. If we find life in Europa's ocean, even simple microbial life, it would tell us that the universe is probably teeming with biology. 2 independent origins of life in the same solar system would suggest that life emerges readily wherever conditions permit. The implications would be staggering. Every star system with water-bearing worlds would become a candidate for biological investigation. On the other hand, if we explore Europa thoroughly and find nothing, no biosignatures, no organic complexity, beyond what random chemistry produces, that would be equally informative. It would suggest that life requires something more than just water and energy. Maybe it needs specific geological context we don't fully understand. Maybe Earth really is special in ways we haven't appreciated. Either answer would be profound. Mars offers a similar potential revelation, but about a different question. Can life survive planetary catastrophe? Mars was once warmer and wetter, with a thicker atmosphere and liquid water on its surface. Something changed. The atmosphere thinned, the water froze or disappeared, and the surface became the hostile desert we see today. If life existed during Mars's clement period, did it go extinct? Or did it retreat underground, adapting to increasingly harsh conditions, clinging to survival in subsurface aquifers or ice deposits? Finding fossilized evidence of ancient Martian life would tell us that life had emerged at least twice in our solar system, just like discovering current life on Europa would. But finding extant life on Mars, organisms still alive today, despite the planet's transformation, would tell us something even more hopeful, that life is resilient, tenacious, capable of enduring catastrophic environmental change. That lesson would have direct relevance to Earth. We're living through a period of rapid climate change driven by human activity. Understanding how life persists through planetary transformations could inform our own survival strategies. What adaptations allow organisms to survive in extremes? How do ecosystems reorganize when their environment fundamentally shifts? Mars could be a natural laboratory for studying these questions on a planetary scale. Let's talk about something that doesn't get discussed enough in the Mars versus Europa debate: the role of time. Not just mission duration or travel time, but geological time, evolutionary time, the vast stretches of cosmic history that shape worlds and the potential life they harbor. Mars and Europa have radically different geological histories, and those histories matter enormously for astrobiology. Mars formed 4.5 billion years ago, like all the planets in our solar system, from the swirling disk of gas and dust that surrounded the young Sun. For its first billion years or so, Mars was a dramatically different world than the one we observe today. Evidence from Martian meteorites, rocks blasted off Mars by asteroid impacts that eventually fell to Earth, tells us that ancient Mars had a substantial atmosphere, probably dominated by carbon dioxide with significant water vapor. This thick atmosphere created a greenhouse effect, warming the surface enough for liquid water to flow. River valleys carved into ancient highlands, minerals like clays and sulfates that only form in the presence of water, and the remnants of what appear to be ancient lake beds all point to a Mars that was once much more hospitable. But something happened between 3.5 and 4 billion years ago. Mars's global magnetic field, which had protected the atmosphere from being stripped away by the solar wind, shut down. Without that protective shield, charged particles from the Sun began stripping away the atmosphere molecule by molecule, a process that continued over hundreds of millions of years. As the atmosphere thinned, the greenhouse effect weakened, temperatures dropped, and liquid water could no longer exist stably on the surface. This transformation didn't happen overnight. It was gradual, giving any life that might have emerged time to adapt, to move underground, to find refuges where water remained liquid in subsurface environments. The key question is whether Mars's habitable period lasted long enough for life to originate in the first place. On Earth, life appears to have emerged relatively quickly in geological terms. The oldest potential biosignatures in the rock record date to about 3.5 to 3.8 billion years ago, when Earth itself was only about 700 million years old. If life can originate that rapidly given the right conditions, then Mars's billion-year window of habitability might have been sufficient. But here's the uncertainty that keeps astrobiologists up at night. We don't actually know how easy or difficult it is for life to begin. We have exactly one example, Earth, and we don't fully understand how non-living chemistry became living biology even on our own planet. Was it inevitable given Earth's early conditions, Or was it improbably lucky, a chance arrangement of molecules that might take billions of years to occur again under identical circumstances? If life is easy, Mars probably had it. If life is hard, Mars might have remained sterile despite its early oceans and temperate climate. We genuinely don't know, and that uncertainty makes Mars exploration scientifically compelling. Every rock we analyze, every drill core we examine, either increases or decreases the probability that we'll find evidence of ancient Martian biology. Europa's story is different in almost every way. While Mars was transforming from a warm, wet world into a frozen desert, Europa remained relatively stable. Its internal ocean probably formed early in the Moon's history and has persisted for billions of years. Unlike Mars, which lost its habitability, Europa maintained conditions suitable for life continuously from the solar system's youth until today. That stability matters enormously. If life requires not just the right ingredients but also sufficient time to organize into self-replicating systems, Europa has had all the time in the world. 4 billion years of liquid water in contact with a rocky seafloor, with chemical energy continuously supplied by hydrothermal activity. If life didn't emerge on Europa given those conditions and that timescale, it would suggest that our understanding of what life requires is fundamentally incomplete. There's another aspect of time worth considering: evolutionary time. Even if simple microbial life emerged on both ancient Mars and Europa, the two environments would drive very different evolutionary trajectories. Mars, assuming life originated during its habitable period, would have faced an extinction-level environmental shift. Any organisms that survived would be those capable of adapting to increasingly extreme conditions: freezing temperatures, desiccation, intense radiation on the surface. Evolution under those pressures would favor extremophiles, organisms specialized for survival in the harshest conditions. We might be looking for microbial communities that have essentially been in survival mode for billions of years, metabolizing incredibly slowly, reproducing rarely, just barely persisting. Europa's life, if it exists, would have evolved in a stable environment where the primary challenges aren't catastrophic change, but rather the inherent difficulties of living in a dark, cold ocean. Evolution there might have produced organisms exquisitely adapted to chemosynthetic lifestyles, perhaps developing sensory systems we can barely imagine, responding to chemical gradients, pressure waves, electrical fields instead of light. 4 billion years is enough time for significant evolutionary complexity to develop. On Earth, multicellular life appeared roughly 600 million years ago after more than 3 billion years of microbial evolution. That doesn't mean Europa would follow the same timeline, but it does mean we shouldn't automatically assume Europa's life, if it exists, would be only simple microbes. Could there be something more complex swimming in Europa's ocean? Genuinely multicellular organisms, perhaps even something approximating simple animals? It's not impossible. The deep oceans on Earth support complex ecosystems around hydrothermal vents despite complete darkness. Fish, crustaceans, tube worms, all thriving on chemical energy at the base of the food chain instead of photosynthesis. Europa's ocean volume is vast, possibly containing more water than all Earth's oceans combined. That's a lot of ecological space. If life established itself and diversified, there could be multiple trophic levels: microbes feeding on chemical energy, slightly larger organisms grazing on the microbes, perhaps even predators hunting the grazers. We're speculating now, but it's informed speculation based on how life organizes itself on Earth when given energy, nutrients, and time. The challenge is that we have no way to know without directly investigating. Remote sensing can tell us about Europa's ice shell, its ocean depth, the chemistry of plume material, but it can't tell us if anything is alive down there. We need to go there. We need instruments in that water. This brings us to one of the most fascinating aspects of the Mars versus Europa question: the different technological pathways they require. Mars exploration builds incrementally on capabilities we've already developed. Each rover is more sophisticated than the last, but the fundamental approach remains consistent. Land on the surface, move around, analyze what you find. Europa demands technological leaps. We've never sent a spacecraft to operate beneath the ice of another world. We've never deployed an autonomous submarine in an alien ocean. These are fundamentally new challenges requiring fundamentally new engineering solutions. The first mission will be risky, expensive, and possibly fail despite our best efforts. But that risk comes with a potential reward that Mars, for all its value, can't offer: the discovery of a completely independent biosphere, a second Genesis, life that evolved entirely separately from Earth's tree of life. If we find that on Europa, we'll know with certainty that we're not alone in the universe. We'll know that life is a cosmic imperative, not a terrestrial accident. Some scientists argue we should focus on Mars precisely because it's easier, accumulating knowledge and capability while developing the technologies we'll eventually need for Europa. Others argue that Europa's potential payoff is so enormous that we should prioritize it despite the challenges, accepting that progress will be slower and more expensive. There's wisdom in both perspectives. The reality is that space exploration isn't a zero-sum game where choosing one target means abandoning another. We can pursue Mars and Europa simultaneously, which is exactly what's happening. Perseverance continues exploring Jezero Crater, while Europa Clipper flies toward Jupiter. The Rosalind Franklin rover is being prepared for its 2028 launch, while scientists design concepts for future Europa landers. The question isn't really which world deserves our attention, both do. The question is how we balance immediate scientific returns against long-term, transformative discoveries. Mars can teach us about planetary evolution, climate change, and the possibility of ancient life. Europa can potentially show us that life is common in the universe, fundamentally changing our perspective on our place in the cosmos. And there's a third option we haven't discussed much yet: Enceladus, Saturn's small moon that also harbors a subsurface ocean and actively vents water vapor into space through geysers at its south pole. Enceladus is even farther than Europa, requiring 7 years to reach instead of 6, but its plumes are more dramatic and accessible. A spacecraft could fly through them repeatedly, sampling ocean material without needing to land at all. Enceladus deserves serious consideration in this conversation, even though it's often overshadowed by Mars and Europa in popular discussions. This tiny moon, only about 500 kilometers in diameter, punches far above its weight class in astrobiological significance. The Cassini spacecraft, which orbited Saturn from 2004 to 2017, revolutionized our understanding of Enceladus during dozens of close flybys. Cassini discovered that enormous plumes of water vapor and ice particles erupt from fractures near Enceladus's south pole, shooting hundreds of kilometers into space. These aren't subtle emissions. They're dramatic geysers visible in images as bright plumes backlit by the sun. More importantly, Cassini flew directly through these plumes multiple times, analyzing their composition with onboard instruments. What it found was extraordinary. The plumes contain water vapor, obviously, but also salt, silica nanoparticles, and most intriguingly, complex organic molecules. We're talking about compounds with carbon-hydrogen bonds, the building blocks of biological chemistry. Later analysis of the Cassini data revealed hydrogen gas in the plumes, probably produced by hydrothermal reactions between water and rock at the ocean floor, exactly the kind of chemical energy that could support microbial life. In 2023, scientists announced the detection of phosphorus compounds in Cassini's plume data, an element essential for life as we know it. Phosphorus is a key component of DNA, RNA, and ATP, the molecule that stores and transfers energy in cells. Finding phosphorus in Enceladus's ocean material was a major discovery because it meant the ocean contains all the essential elements for life: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. From a purely astrobiological perspective, Enceladus might be an even better target than Europa. The plumes give us direct access to ocean material without drilling through kilometers of ice. A dedicated Enceladus mission could fly through the plumes dozens of times with instruments specifically designed to detect biosignatures, complex organic molecules in specific ratios that would be hard to explain without biology. Maybe amino acids with a preference for left-handed or right-handed forms like Earth's life exhibits, perhaps even cellular structures or membrane fragments. The case for an Enceladus life detection mission is scientifically compelling. So why does Europa get more attention and funding? Part of it is timing and momentum. Europa Clipper was already in development when some of the most exciting Enceladus discoveries were announced. Cancelling a mission that's already being built and shifting resources to a new target creates delays and wastes the investment already made. There's also the matter of ocean size and complexity. Enceladus's ocean, while real and accessible, is much smaller than Europa's, probably only about 10 kilometers deep, with a total volume a fraction of Europa's ocean. A smaller ocean means less ecological space, fewer potential niches for life to diversify, and possibly simpler ecosystems if life exists at all. Europa's vast ocean could potentially support more complex and diverse biology simply because there's more room for evolution to experiment. Think of it like comparing a small pond to the Pacific Ocean on Earth. Both can support life, but the Pacific offers vastly more diversity, more ecological complexity, more opportunities for interesting biology to develop. Still, if the primary goal is simply detecting whether extraterrestrial life exists, Enceladus offers the most direct path to an answer. You could get definitive results with a relatively low-cost mission consisting of a spacecraft designed purely to fly through plumes and analyze what it catches. No landers, no drilling, no autonomous submarines, just repeated sampling passes with state-of-the-art instruments. NASA is considering exactly this kind of mission. The Enceladus Orbilander concept would orbit Saturn, making multiple passes through Enceladus's plumes before eventually landing on the Moon's surface to conduct detailed studies of the ice and search for any organic material deposited by the plumes. The mission could launch in the late 2030s, arriving at Saturn in the mid-2040s. That timeline seems distant, but it's actually reasonable given the complexity of outer solar system missions. These aren't quick trips. The journey takes years, the mission development takes years, and the scientific analysis continues for years after data returns. Space exploration operates on timescales that test human patience but align perfectly with the geological and cosmic processes we're studying. So now we have 3 targets: Mars, Europa, and Enceladus. Each offers unique opportunities. Mars is accessible and might preserve evidence of ancient life. Europa has the largest potentially habitable ocean in the solar system. Enceladus gives us direct sampling of ocean material through its plumes. How do we choose? The honest answer is that we don't have to choose. Space agencies around the world are pursuing all 3. The exploration of our solar system isn't a single narrative with one destination, it's multiple parallel investigations, each building knowledge, each answering different questions about how planets and moons evolve and whether life is unique to Earth. But there's a deeper question beneath all this. What are we really searching for? Are we looking for microbes, simple, single-celled organisms that would prove life exists beyond Earth? Or are we hoping for something more, something complex enough to feel like a genuine discovery of alien life rather than just alien chemistry? This distinction matters because it affects how we design our missions and interpret our results. Detecting microbial life is extraordinarily difficult. On Earth, we can identify microbes through direct observation with microscopes, through culturing them in laboratories, through analyzing their DNA. None of those techniques translate easily to robotic exploration of other worlds. A Mars rover can't carry a microscope powerful enough to see individual bacterial cells, and even if it could, distinguishing between a microbial fossil and a weirdly shaped mineral grain is notoriously difficult. Some of the oldest claimed fossils on Earth remain controversial, despite being studied in laboratories for decades. Imagine trying to make that determination with a robot arm and a camera millions of kilometers away. We rely instead on biosignatures, indirect evidence that life is or was present. These might include specific ratios of isotopes that living organisms prefer, complex organic molecules that are hard to produce abiotically, or patterns in rock that resemble microbial colonies. But biosignatures are tricky because we're pattern-seeking creatures. We see faces in clouds and animals in constellations. We can convince ourselves we've found evidence of life when we're actually seeing random geological processes. The most famous example of this problem is the Allen Hills meteorite, designated ALH 84001. This chunk of Martian rock was found in Antarctica in 1984, and in 1996 a team of scientists announced they had found potential evidence of fossilized Martian bacteria inside it. The announcement made headlines worldwide. President Clinton gave a speech about the profound implications, but subsequent analysis by other researchers cast serious doubt on the claims. The supposed microfossils could be explained by non-biological processes. The organic molecules might have been terrestrial contamination. The magnetic crystals that seemed biological in origin could form through chemistry alone. Today, most scientists are skeptical that ALH 84001 contains evidence of Martian life, though a few researchers still defend the original interpretation. This controversy illustrates the challenge we face. Even with a Martian rock sample in Earth laboratories, analyzed with our most sophisticated instruments by expert scientists, we can't reach consensus on whether it contains biosignatures. How much harder will it be to make that determination with data from a rover on Mars or a submarine in Europa's ocean? This is why some researchers argue for prioritizing sample return missions. Bring Martian rocks back to Earth, where hundreds of laboratories can analyze them using techniques that would be impossible to miniaturize for a rover, collect ice samples from Europa or plume material from Enceladus, and return them for detailed study. Sample return eliminates ambiguity by allowing the full power of terrestrial science to be brought to bear on extraterrestrial materials, but sample return missions are expensive and technically challenging. They require not just getting to the target world, but also getting back, which often means multiple spacecraft, one to collect samples, another to rendezvous in orbit and carry them home. The recently cancelled Mars sample return program was projected to cost over $10 billion. A Europa sample return would be even more expensive, given the greater distance and harsher environment. We're forced into a trade-off between certainty and cost. In situ missions, where the spacecraft stays at the target and conducts investigations there, are less expensive but provide less definitive results. Sample return missions are more expensive but offer higher confidence in our conclusions. Neither approach is clearly superior. Both have roles to play. There's another dimension to this discussion that we need to address: planetary protection. This might sound like science fiction, but it's a serious consideration governed by international treaties and national regulations. Planetary protection refers to the protocols we follow to prevent biological contamination, both of other worlds by Earth life and of Earth by potential extraterrestrial life. The logic is straightforward. If we're searching for life on Mars or Europa, we need to ensure we're not finding microbes we accidentally brought from Earth. Spacecraft are built in clean rooms, but perfect sterilization is nearly impossible. Bacteria are incredibly resilient. Some can survive extreme radiation, temperature swings, and the vacuum of space. There's documented evidence of microbes surviving on the Moon for years inside equipment from the Apollo missions before being brought back to Earth. Before any spacecraft launches to a potentially habitable world, it undergoes rigorous cleaning and, in some cases, sterilization through heat or chemical treatment. The level of cleaning depends on the mission's trajectory and goals. A spacecraft that will orbit Mars requires less stringent treatment than a lander that will touch the surface and drill into the ground. A mission to Europa's ocean would require the most careful sterilization we can achieve, because contaminating that pristine ocean with Earth microbes would be scientifically catastrophic and ethically questionable. But here's the difficult truth: we can't guarantee complete sterilization without potentially damaging the spacecraft's electronics and instruments. Heat sterilization, the most effective method, can melt solder joints, crack circuit boards, and degrade sensitive components. Chemical sterilization might leave residues that interfere with instruments designed to detect organic molecules. There's an inherent tension between maximally protecting other worlds and building functional spacecraft. NASA and other space agencies navigate this tension through statistical approaches. They calculate the probability of contamination and ensure it remains below established thresholds. For Mars, current guidelines require that there's less than 1 in 10,000 chance of contaminating a region where life might exist. For Europa, the standards are even stricter because the entire ocean is considered a special region, requiring maximum protection. This is one reason why Europa Clipper doesn't land on the surface. By remaining in orbit and only conducting flybys, the spacecraft avoids direct contact with the ice shell and eliminates any risk of contaminating the ocean below. A future Europa lander would need extraordinary sterilization efforts, probably including components that are heat-treated to temperatures that kill all known Earth microbes, even the most resilient bacterial spores. There's also the reverse concern, protecting Earth from potential extraterrestrial organisms. This sounds far-fetched until you consider what a returned sample from Mars or Europa might contain. If we brought back ice from Europa and it actually harbored living microbes, those organisms would be fundamentally alien, products of a completely separate evolutionary history. We'd have no idea how they might interact with Earth's biosphere if they escaped containment. The probability of extraterrestrial microbes being dangerous to Earth life is probably low. They evolved in completely different environments for completely different conditions. They'd likely struggle to survive in Earth's environment, much less compete with billions of years of highly adapted terrestrial organisms. But probably low isn't the same as zero, and the consequences of being wrong could be catastrophic. This is why sample return missions would require biosafety containment at levels currently used only for the most dangerous terrestrial pathogens. The samples would be stored and analyzed in facilities with multiple layers of physical containment, sterilization protocols for anything leaving the facility, and strict controls on who can access the materials. Building such a facility would be a significant portion of a sample return mission's cost. Some scientists argue that these planetary protection protocols are overly cautious, that we're imposing unnecessary costs and constraints based on vanishingly small risks. They point out that material from Mars regularly reaches Earth naturally through meteorites without causing any apparent problems. If Martian microbes exist and pose a threat, they've had billions of years to hitch rides on ejected rock fragments. Why should we treat carefully contained samples any differently? The counter-argument is that natural transfer and deliberate sample return are fundamentally different scenarios. Meteorites experience extreme heating during atmospheric entry, potentially sterilizing any organisms on or near their surfaces. Returned samples would be carefully protected from such sterilization to preserve their scientific value. We'd be deliberately bringing potentially living material from another world, which has never happened naturally in Earth's history, at the scale and under the conditions a sample return would entail. I find myself persuaded by the cautious approach. The scientific cost of excessive caution is that missions become more expensive and take longer to implement. The potential cost of insufficient caution, while admittedly improbable, could be ecological disaster. When the downside risk includes scenarios like disrupting Earth's biosphere, even low-probability risks deserve serious mitigation efforts. This brings us back to the comparative analysis of Mars and Europa. From a planetary protection perspective, Mars is somewhat easier to work with. We've already landed numerous spacecraft there. We have decades of experience with Mars-appropriate sterilization protocols, and the natural exchange of material between Mars and Earth through meteorites provides some reassurance that we're not encountering something entirely outside Earth's historical experience. Europa is pristine in a way Mars isn't. No Earth material has naturally reached Europa's subsurface ocean. If life exists there, it has evolved in complete isolation from Earth's biosphere for the entire history of the solar system. Contaminating that environment with Earth microbes wouldn't just be bad science. It would be the destruction of a unique natural laboratory, possibly the only chance we'll ever have, to study a truly independent biosphere in our solar system. This is why some scientists propose that we should never send anything to Europa's ocean that hasn't been completely sterilized, even if it means limiting what kinds of missions we can conduct. Others suggest that the scientific value of a Europa submarine outweighs the contamination risks, especially if we take reasonable precautions. It's an ethical debate as much as a scientific one, involving questions about our responsibilities to extraterrestrial environments and potential life forms. These considerations don't apply only to government space agencies. As private spaceflight becomes more capable, companies like SpaceX talk about establishing human settlements on Mars. Elon Musk has repeatedly stated his goal of creating a self-sustaining city on Mars with 1 million people by the end of the century. That vision is ambitious, possibly unrealistic on that timeline, but it raises profound planetary protection questions. Humans are walking contamination factories. We shed millions of skin cells daily, we exhale bacteria and viruses, we excrete microbes in our waste. A human settlement on Mars would release countless Earth organisms into the Martian environment despite any containment efforts. If we're serious about searching for indigenous Martian life, shouldn't we avoid human missions until we've thoroughly surveyed the planet robotically? But that position faces a practical objection. Waiting for definitive proof of Martian life's absence could take centuries. Mars is an entire planet. Even with aggressive robotic exploration, we can only sample tiny fractions of its surface and subsurface. Proving absence is fundamentally harder than proving presence. Do we really want to delay human exploration indefinitely based on the possibility that we haven't looked everywhere thoroughly enough? There's a middle position that many planetary scientists support. Focus human activities on regions of Mars that are clearly inhospitable to any potential Martian life, while designating certain areas as special regions where only carefully sterilized robotic missions can operate. Establish settlements in the dry, radiation-blasted equatorial regions while protecting subsurface ice deposits and potential aquifers in the mid-latitudes. This approach isn't perfect. Microbes from human settlements could potentially spread through dust storms or underground water movement. But it balances the scientific imperative to search for life with the human impulse to explore and expand. Perfect protection is impossible once humans arrive. Reasonable protection might be the best we can achieve. Europa doesn't face this immediate dilemma because no one is seriously proposing human missions to Jupiter's moons in the foreseeable future. The radiation environment alone makes it prohibitively dangerous for human explorers. Any Europa mission we launch in the next several decades will be robotic, which allows for much stricter contamination control, but even robotic missions must grapple with difficult questions. If we develop a cryobot and submarine capable of reaching Europa's ocean, should we send it? The scientific payoff could be revolutionary, but the contamination risk, however small, is real. Or should we restrict ourselves to orbit and plume sampling indefinitely, accepting limited data to guarantee we don't contaminate that pristine ocean? I don't think there's a universally correct answer. It depends on how you weigh different values. The scientific value of direct exploration versus the ethical imperative to preserve extraterrestrial environments. The probability of contamination versus the magnitude of potential consequences. The benefit to human knowledge versus our responsibility to potential alien life forms. If you made this far, make sure to give this video a like. If you enjoyed this video, I am sure you will love this other on the screen. What would life on Mars really be like? What makes abandoning everything for a frozen, radiation-soaked desert worthwhile? See you there.